This is our video on effusion, diffusion, and we'll talk about non-ideal behavior of gases at the end. I wanted to review kinetic molecular theory really quick because a few of these things are going to be really important to the conversations we're about to have. The one I want to start with is this first one. It says gases consist of molecules that are in continuous random motion. We're going to keep that in mind when we start talking about how gases move between spaces. And the next one is that the average kinetic energy of a gas is constant as long as T remains unchanged, so as long as temperature is also constant. And then this last one, that the average kinetic energy is proportional to the absolute temperature. So let's keep those in mind while we look at some data. This is a graph of molecular speed and the number of molecules that are going that speed. It got a little cut off down here at the bottom, so I'm going to write in what it would have said. It says molecular speed, and the units are meters per second. And the numbers here should have been 200, so that's 200 meters per second, 400, 600, 800. And let's focus on the blue line first. What this is showing is that a few molecules are going really slow, and this is at 25 degrees. As we get a little faster, more molecules are going a little faster. Most molecules are going somewhere in about the 400 meters per second range. And then less molecules of O2 are going these higher speeds because we're only at 25 degrees. Now let's look at this red curve here. And what it's looking at is the number of O2 molecules that are going certain speeds when the sample is at 1,000 degrees, so much higher temperature. And what we see at 1,000 degrees is some are going low speeds, most are going about 800 meters per second there, and some are going really high speeds, but not that many. Now overall, what this graph is showing us is that most O2 molecules are going about 400 at 25 degrees. Most O2 molecules at 1,000 degrees are going about 800, so much faster. So as the temperature goes up, the speed goes up. I just went back to our review of kinetic molecular theory slide, and I want to look at this one down here at the bottom. It says that the average kinetic energy is proportional to the absolute temperature. And we also just learned from that graph that temperature and speed are related. As the temperature goes up, speed goes up. Now this postulate is also saying that kinetic energy is related to temperature and it's proportional. So if T is going up, kinetic energy is also going to go up. So when you put those things together, there's an equation that talks about the relationship between kinetic energy and speed. Okay, this is the equation that kinetic energy is equal to 1/2 the mass of the particle, and V is velocity, so that's the same thing as speed. And what we can see here is that if we increase the velocity, the kinetic energy is going to go up, and it's going to have a huge effect because when we increase the velocity, it's squared. So that means that the kinetic energy is going to go up exponentially. Okay, here we have another graph, and again, it got cut off at the bottom, so I'm going to write what was there at the bottom. It just said molecular speed again, and the units are in meters per second. And this is 500, this is 1,000, and this is 1,500 here, and out here would have been 2,000. All right, so what we're looking at is we're looking at different molecules and what kind of average molecular speed they would have. They're all at the same temperature. Let's look at the trend that's here. Oxygen gas, its average, the highest, where it has the most molecules, its average molecular speed is maybe something about, 300. Nitrogen is maybe 400. Oxygen, we'll call that 500. And then helium out here, we'll call that 1250. I cleaned that up a little bit, but what we can tell when we're looking at these numbers is that oxygen is going on average a lot slower than helium is at the same temperature. Now these molecules aren't that different in size. I guess helium is quite small than an oxygen gas, but oxygen isn't huge compared to helium as far as space goes. But what the big difference is their molar masses. Oxygen is 32 grams per mole. Nitrogen's about 28 grams per mole. Water is 18 grams per mole. And helium is 4 grams per mole. So what we're seeing is that as the molar mass goes down, the speeds are going up. Now, if we keep that relationship in mind, that as mass goes down, the speed goes up, we can tie that back to our kinetic energy equation. It works because at any given temperature, molecules of all gases have the same average kinetic energy. So what we're saying is that we're keeping kinetic energy constant because temperature isn't changing. All those molecules were at the same temperature. And as the mass goes down, it means the velocity, the speed, had to go up so that we could keep kinetic energy constant. What that means is that the relationship is always going to be that molecules of a higher molecular weight, so those are the heavy molecules, will always have lower molecular speed. And light molecules, molecules of a lower molecular weight, will always have a higher molecular speed. So the heavier always means that they're going to be going slower. Lighter means that they're going to be going faster. It's going to be an important relationship when we talk about how gases behave moving through space. And there's two situations that I need us to look at. I'm going to draw a line between them here. The first one is the idea of effusion. Effusion is a very special set of circumstances where you have kind of a high concentration of gas blocked by what we call an aperture, or sometimes we call it a frit. It's a barrier, basically, and that barrier has a small hole in it. And that small hole is about the size of one of the gas particles, and that creates a situation in which particles can make it through, but they only make it through once in a while, and it has to do with statistics. So the more that they're moving around, the more they're going to bounce around like this, and they're just going to happen to hit the top and then bounce down and make it through, like we see this one has here. So the more that they're moving around, the more likely it is that one will make it through the hole, or more will make it through the hole. Right. The other one that I want to talk about is diffusion. Diffusion is a situation you're probably much more familiar with. Diffusion is just when something of higher concentration, so we have our ink here, okay, higher concentration, spreads out through open space. So this is ink spreading out into water, but this would be like if you dumped or if you opened a container of gas into another container of gas. The gas particles would just randomly move through the open space, and they would spread out in every direction pretty much equally. Now, if you'd like to see a picture of a gas diffusing, it can be kind of hard to do because a lot of our gases are clear and colorless. So even when we mix them together, it's hard to track how they're mixing together because we can't tell one from the other. But we have a special gas. We have bromine gas, which is kind of a dark amber orange, and that is in this flask right here. And right now it's capped, so none of it's going to be able to leak out. But if you open that flask, so we're going to open the flask, we're going to take the cork out. What happens is the gas spreads out in all directions, so the whole entire container gets filled, and that's diffusion. Now, the rate of diffusion is guided or controlled by some kind of principles here. Really, it has to do with how dense the gas on the outside is compared to how dense the gas on the inside is, and how fast each one of those molecules is moving. But because a fusion is a much more controlled situation, it's governed by this law called Graham's law, and it says that the rate of diffusion of a gas is proportional to this here. And let me just explain what that means. This is the speed, and that RMS means root mean squared. And really, it's just a way to symbolize an average. So it's not exactly the same, but when we see this URMS, we're going to just think average speed. So the rate of diffusion of a gas is proportional to its speed. And that's what this equation here is saying. It's saying that the rate of diffusion is proportional to its speed, and speed is proportional to the square root of 1 over the molar mass. Now, what this tells us is that heavier gases will effuse slower than lighter gases. If I go back to my picture of a fusion, and we just say that heavier will effuse less. Let's try and explain that. If a gas particle is heavier, it's going to be slower. And if it's moving around slower, it's going to be bouncing around, but very slow. And there's going to be less of a chance that over a certain period of time, one's going to make it through that hole. If they're moving around a lot faster, there's so many happening in here that just statistically more are going to make it through the hole. So it really has to do with the fact that heavier gases are moving slower, and when they're moving slower, there are less collisions, and less collisions means that there's less likelihood that it will have the right collision to make it through that hole. Now again, I've just written out what this relationship means here again. The rate of diffusion is proportional to speed, and speed is proportional to 1 over the molar mass. Now, what's nice about Graham's law is that it basically says that if you can measure the rate of diffusion, you can calculate something's molar mass. And that's a way that you can use Graham's law. Another way is that you can set up an equation where you're comparing two rates of diffusion, and then you're comparing two molar masses. And that's how we have it written here. What this is saying is the rate of diffusion for gas 1 divided by the rate of diffusion for gas 2 is equal to the square root of their molar masses. So this is the molar mass of gas 2, and this is the molar mass of gas 1. So this is an equation where we can measure the rate. So this is an equation that we can use where we can measure the rate of effusion of one gas, we can know the molar mass of that gas, and then if we can measure the rate of effusion of a second unknown gas, we can find that gas's molar mass. So let's do a practice. I'm going to read through the problem, and I'm going to kind of pay attention to what numbers I have and what variables I need. It says that we have carbon dioxide, and it effuses. Anytime we see that word effuses, it probably has to do with Graham's law. And it says it effuses through a pinhole, and its rate is 232 milliliters per minute. Then another gas effuses at a rate of this. So it looks like I have two rates. The first rate, the rate of carbon dioxide, was 232 milliliters per minute, so a volume per minute. My second rate is the rate of, it just says another gas, I'm going to say an unknown gas, is 0.363 milliliters per minute. Now, just looking at these, before we do the rest of the problem, just looking at these two rates, because this rate is higher, that gas effuses faster, so more per minute, I know that that gas must be traveling faster, and so I know that that gas must be lighter than carbon dioxide. And I'm going to keep that in mind when I actually get my number here, because this problem is saying what is the molar mass of the gas. When I actually get my answer, I'm just going to make sure that the unknown gas was a lighter gas, that I was able to calculate that. Okay, so the problem says, what's the molar mass of a gas? And I know that I can use the comparative version of Graham's law, where I'm comparing two gases to each other. Now again, I'm comparing two rates on this side, which I have. Okay, so I have the rate of carbon dioxide, I have the rate of my unknown. I can find out the mass of carbon dioxide because I know the molar mass of carbon dioxide is 1 carbon and 2 oxygens, and that comes out to be 44.01 grams per mole. So I have this one. So I have everything that I need to find the molar mass of my unknown. The next thing that I'm going to do is I'm just going to rearrange this equation so that I get the mass of the unknown on one side, and I get everything else on the other. So I'm just going to square both sides to get rid of that square root. Okay, and then I want to get rid of this mass of CO2, so I'm going to multiply, so those cancel out, and that'll go over there. Okay, the last thing that I have to do is actually put my numbers in there. So the rate of CO2 is 0.232 milliliters per minute. The rate of the unknown is 363. I'm going to square that, and then I'm going to multiply it by 44.01 grams per mole, which is the molar mass of carbon dioxide. All right, on my calculator, I got 18.0 to 3 sig figs, and that would be, so milliliters per minute and milliliters per minute, even when you square them, you're squaring both of them, so those are going to cancel out, and our units are grams per mole. Okay, if you can think of any maybe gas molecules that you know are about 18 grams per mole, a really familiar one is water. We don't know for sure, but water would be probably a pretty good guess. And then if I'm comparing to what I said over here, I said that my unknown would be lighter than carbon dioxide, okay? And 18 is lighter than 44. So that does make sense kind of with the concepts we were talking about Graham's law. The last thing that I want to talk about in this video is what happens when gases behave non-ideally, or another way of saying that is what would cause a gas to not behave as an ideal gas. When we started this video, we reviewed the postulates of kinetic molecular theory. We talked about how gases are moving totally randomly, that their kinetic energy is proportional to temperature and Kelvin. Another one that was on that list is that gases have a very small volume compared to the volume of the entire sample of gas. And really what we're saying there is that the amount of empty space between particles is huge. All this space that's between all these particles is very big compared to just the gas particles themselves. And that means the gases are really compressible and that they don't really feel any intermolecular forces or any attractions between other particles because they're so far apart from each other. But what happens when the gas particles aren't that far apart from each other? Let's think about reasons why that would happen. So one of the reasons why gas particles might not be that far apart from each other is that each one is individually bigger. So these would be like, I'm drawing these gas particles. They're huge gas particles, something like proteins or just really big molecules. And because they're really big themselves, the space between them isn't that much. And that would be a way that gas particles would feel interactions with each other. The problem with this is that honestly, gas particles tend not to be things like proteins. Those molecules are so heavy, and due to their intermolecular forces that we'll learn about in chapter 11, they just tend not to be gases in the first place. So most gas particles aren't big enough so that they take up a lot of room. But another way that there would be less space between the gas particles is at very high pressures and low temperatures. The molecules, the high pressure means that we are squeezing the particles together, and the low temperatures means that they aren't moving around very much. So under these circumstances, we can get particles pretty close to each other, and when they get close to each other, they start feeling attractions to each other, and that really changes the way that they behave, and they behave what we call non-ideally. And when we talk about non-ideal behavior, it means any time that a gas doesn't follow one of those 5 tenets that we talked about in the beginning of this video. So anytime the gas particles are not moving totally randomly, anytime the gas particles actually feel attraction to each other, anytime the gas particles are not very small compared to the space between them. And those behaviors happen when the particles are really close to each other. So again, at high pressures, when they're squeezed together, and at low temperatures, when they're not moving very much, they tend to break those rules the most. So in situations that the pressure is so high that a lot of molecules are packed into a small space, we would consider that a very high pressure. And in that situation, the molar volume, the amount of space that a gas should take up, is actually higher than what we would predict by the ideal gas law. So we can calculate a volume, but the real volume is actually going to be higher. So that's what can happen at high pressures. A different situation is low temperatures. And at low temperatures, the molecules are moving slowly, and so slow enough that they can be affected by intermolecular forces. I kind of think about this as that they're moving slow enough that they can kind of stop to smell the roses around them. They can kind of stop to feel the interactions around them. And this means that the intermolecular forces are actually going to become significant. And we haven't really talked about that word intermolecular forces. That's going to be chapter 11 for us. But intermolecular forces are attractions or repulsions between particles. And when molecules feel intermolecular forces, it means that they're not moving totally randomly. If there are attractive forces, they're going to come closer together. And if there are repulsive forces, they're going to move further apart. But neither one of those things is behaving randomly. If the molecules feel attractive forces, so attractive intermolecular forces, it can mean that the pressure would be lower than what we would actually predict by the ideal gas law. And if we see molecules with repulsion forces, so repelling forces, it would make the pressure higher than what we would calculate by the ideal gas law. So 2 situations in which gases behave non-ideally is at high pressures and at low temperatures. And when we say high pressures, we mean pressures that are like, in a volcano, in a sun, something like that, not something that we would kind of find anywhere where humans would live. And at low temperatures, we're talking about so low that we are out in the middle of space, something close to 0 Kelvin. In this video, we talked about kinetic energy, its relationship to speed and temperature. We also talked about effusion and diffusion. And we talked about how we can use Graham's law to find the molar mass. And then we finish it up with talking about non-ideal behavior.